So as I was trying to make solutions to problem, I think it was 41 on the practice test, it occurred to me that a lot of the linear algebra problems that you'll see on this test can be answered by thinking of a few different examples. So what I thought I'd do in this video is just go over those examples. Give you, 5 or 6 or 7 different matrices and talk a little bit about what those transformations would look like, trying to pick on the ones that are the most intuitive so that they'd be easy to remember. The hope being kind of twofold, that you could use those examples to answer questions on your test, but also that these examples would kind of strengthen your overall understanding of linear algebra, perhaps allowing you to answer other linear algebra questions. So anyways, without further ado, some of the first examples of linear transformations that come to mind for me are projections, rotations, scaling, and shearing. So maybe this is going to turn into like a chart or something. We'll see how it goes. Let's start with projections. One projection you can think of is just the projection that takes an arbitrary vector xy and projects it down onto the x-axis. So the new y-coordinate is 0, takes it to x0. The matrix representing this projection, maybe I'll subscript it P2, because later I'll look at projections in 3 dimensions. So the matrix P2 would have column vectors of 1, 0, and 0, 0. And as you can verify, applying this matrix to this vector would leave you with this vector. The way to think about it is it takes the basis vector 1, 0 and leaves it at 1, 0. And it takes the basis vector 0, 1 and takes it to 0, 0. Want a picture? Sure. Here's my 2-dimensional space. Here's some arbitrary vector. The image of this vector under this transformation would be this vector here. If we solve for the eigenvalues, which I won't do in each of these examples, but maybe I'll do it once just to sort of illustrate the process. Eigenvalues and eigenvectors come from this equation. T is your matrix, V is your eigenvector, lambda is your eigenvalue. The way to think about them is they're vectors that don't get knocked off their span by the transformation. So they're vectors that when you apply the transformation to them, end up pointing in the same direction, just get longer or shorter. And that same direction idea is a bit of a misnomer because they could be going backwards, but they'd still be on the same line. The way you solve for these guys, a little bit informally, is you set the equation equal to 0, factor a v out, and then recognize the only way we're going to have solutions to this equation is if the determinant of t minus lambda is equal to 0. It's a good idea to talk yourself through all these different steps, maybe even point out to yourself how I'm being a little bit informal, allowing myself to subtract a scalar from a matrix, for example, but really understanding why each of these lines makes sense. Maybe the most important is going from here to here. This is just a matrix, so it's a transformation, and when I apply this transformation to this vector, I end up with the 0 vector. There's 2 ways that can happen. Either the vector itself is the 0 vector, or the determinant of this matrix equals 0. Since we don't allow eigenvectors to be the 0 vector, we can solve for eigenvalues by considering the determinant of our matrix minus lambda. So in this example up here, if I subtract lambda, really lambda times the identity matrix, I need to subtract lambdas from the diagonal. So I'd get 1 minus lambda and negative lambda on the diagonals. If I look for the determinant, it's the difference in the product of the diagonals. So 1 minus lambda times negative lambda minus the product of 0 and 0, which is just 0. It's easy enough to solve when this equation equals 0. That'll happen if lambda equals 1 or if lambda equals 0. If lambda equals 1, then P2 minus lambda would be equal to 0, 0, 0, negative 1. So remember up in this line, we're looking for vectors, which we can multiply by this matrix and get 0 as the product. Well, x is a free variable, so we can make that whatever we want. In order to get a 0 in this position, y must be equal to 0. What I'm saying is that when lambda equals 1, a vector that would be a solution to this equation would be 1, 0. This is the eigenvector corresponding with this eigenvalue. Oh yeah, that makes sense. If I started out with this vector in blue and applied this transformation, I'd end up with just this vector in blue because it's already on this axis. This depicts the vector in blue. Applying the transformation t to this vector leaves me with just some scalar multiple of this vector. In this case, it's a scalar multiple of 1. The length of the vector in blue would not change. As we saw up here, we also have a solution when lambda equals 0. So we have 2 different eigenvalues. An eigenvector corresponding with this eigenvalue would be 0, 1. You can confirm that algebraically, or you can just sort of think about this vector right here. If I applied this transformation, would end up right here at the 0 vector, which is just a scalar multiple of the original vector. How much are you scaling it by? You're multiplying it by 0. The fact that lambda equals 0 is an eigenvalue means that this matrix is not invertible. Oh yeah, that makes sense. It's projecting a 2-dimensional space to a 1-dimensional space, So it couldn't possibly be invertible, because if it were invertible, its inverse would have to take a one-dimensional space back to a two-dimensional space, and that can't happen. It wouldn't be well defined. The rank of this matrix is equal to 1 because the dimension of the image is 1 because we're projecting down onto the x-axis. The nullity of this matrix is also 1. That's because the dimension of the null space is 1. That's because all the vectors on the y-axis project down to the origin. We have one dimension that goes to the 0 vector. Note the rank plus the nullity equals 2, which is the dimension of the domain here. That's always true. That's called the rank nullity theorem. In this case, 2 equals 1 plus 1. We can also think about projections in 3 dimensions. So we could take a vector x, y, z down to maybe, I don't know, x, y, 0. That matrix would look pretty similar. The basis vector 1, 0, 0 would go to 1, 0, 0. The basis vector 0, 1, 0 would go to 0, 1, 0. But the basis vector 0, 0, 1 would go to 0, 0, 0. Maybe we'll call this P3. It's a projection from 3 dimensions to 2 dimensions. As you can verify, we're going to have the same eigenvalues, 0 and 1. I guess I listed 1 first above, so I'll do that again. The fact that 0 is an eigenvalue, again, tells us this is not invertible. But of course, we knew that because the rank of this matrix is only 2. The nullity is 1. Again, we see that 2 plus 1 equals 3. The nullity is 1 because all of the vectors on the z-axis map to the origin. All right, if you start out with 0, 0, 3, that goes to 0, 0, 0. Solutions to our eigenvalue equation when lambda equals 1 are of the form x, y, 0, as you can verify. So we can think of 1, 0, 0 and 0, 1, 0 as two of the eigenvectors. You take 1, 0, 0 and you project it, it's going to end up at 1, 0, 0. In other words, it's going to leave it unchanged. Another way of thinking about that is we'll just scale it by multiplying it by 1. Same idea for, I don't know, 0, 7, 0, which this projection would take to 0, 7, 0. The eigenvalue at 0 corresponds with an eigenvector of 0, 0, 1. That's just saying that any vector on the z-axis gets mapped to the origin. That's why our nullity is equal to 1. Maybe a little bit faster. Let's talk about rotations. These can be really good counterexamples. Again, we'll start out in 2 dimensions. Supposing we want to rotate counterclockwise by an angle of theta. Our rotation matrix is just cosine of theta, sine of theta, negative sine of theta, cosine of theta. So all we're doing here is starting out with some arbitrary vector xy and ending up with some new vector of the same length. Hopefully I'm drawing that the same length so that this angle right here is theta. Maybe I'll call this new point x prime, y prime. If you take the time to calculate the eigenvalues using the same process we did over here, you'll get cosine of theta plus I sine of theta and cosine of theta minus I sine of theta. Note that this only gives you a real value of sine of theta equals 0. And as you may remember from a trig class, that happens when theta is a multiple of pi. So unless we're talking like a 0-degree rotation or a 180-degree rotation or something, we're not going to have any real eigenvalues. Oh yeah, that makes sense. If we rotate everything, I don't know, like 100 degrees like we did in this picture, give or take, there won't be any non-zero vectors that end up as scalar multiples of themselves. Note that this matrix is invertible. All we got to do is rotate back in the other direction. The rank of this matrix is 2. The nullity is 0. Good little check that that satisfies our rank nullity theorem. I guess we should also consider a rotation in 3 dimensions. Maybe we'll rotate around the x-axis. What that matrix would look like is very similar to what this matrix looks like, except our first row and column are 1, 0, 0. And then we kind of append the 2 by 2 matrix above right here. So cosine of theta, sine of theta, negative sine, cosine. If we're rotating about the x-axis, maybe you can kind of visualize that in your head. Most of the vectors would get knocked off their span by this transformation. Again, assuming theta isn't 0 or 180 degrees or something. But there's some vectors that would not. All of the vectors on the x-axis, on the axis of rotation, would stay on that axis of rotation. For that reason, 1, 0, 0 would be an eigenvector, because when we rotate around the x-axis, scalar multiples of this vector don't get longer or shorter. Lambda equals 1 is the corresponding eigenvalue. Again, this matrix is invertible, maybe easily invertible. Just rotate back the other direction. Maybe the simplest matrix, maybe I should have started here, is just scaling. So here we're taking a vector like xy, and we're mapping it to some multiple of xy. So maybe ax, ay. I guess we could make it a little bit more general. We can make it ax, by. Sure. What that matrix would look like. Maybe I'll call it M2 because we're just multiplying and we're in 2 dimensions. That saves me the letter S for shearing over here. Would be A0, 0, B. You can verify, multiply this by xy, and see that this is what you end up with. Think about what vectors would end up as just scalar multiples of themselves. Well, all of the vectors on the x-axis certainly would. So 1, 0 would be an eigenvector. If you're on the x-axis, your y-coordinate is 0. So this b doesn't come into play. All that happens is your x-coordinate gets multiplied by a, so the eigenvalue corresponding with this eigenvector would be whatever number a is equal to. Similarly, b is an eigenvalue corresponding with the eigenvector 0, 1. Note that if we chose a and b to be the same number, then we'd only have one eigenvalue and two eigenvectors corresponding with that eigenvalue. When multiple choice questions talk about distinct eigenvalues and the number of linearly independent eigenvectors corresponding with those eigenvalues, sometimes it's as easy as messing with this example to either prove the statement or come up with the counterexample. Let's see, the rank here would be 2, because the image of this transformation is still two-dimensional. The nullity would be 0, because the dimension of the null space is 0, because the only vectors that get mapped to the 0 vector is the 0 vector itself, assuming that a and b do not equal 0. Note that if either a or b equals 0, then we end up with the projection. So lambda equals 0 would be an eigenvalue, so the matrix would no longer be invertible. However, as long as a and b themselves are not equal to 0, the matrix is invertible. We can do this in 3 dimensions as well. Maybe this time I'll scale by the same amount in 2 of the dimensions. So a, 0, 0, 0, a, 0, and then 0, 0, b. Sure. My eigenvalues are again going to be a and b. The eigenvectors corresponding with this eigenvalue of a would be two-dimensional with basis vectors 1, 0, 0 and 0, 1, 0. The eigenvector corresponding with the eigenvalue of b would be 0, 0, 1. The rank is 3, the nullity is 0, and we're easily invertible. Again, here I'm assuming that a and b do not equal 0. Finally, shearing. What shearing does, or one example of shearing, would be if I took the vector xy and I mapped that to x plus y, y. Maybe I'll call this S2. One example of a shearing matrix would be 1, 0, 1, 1. What's going on over here might be easiest to see if we just consider the image of the vector 0, 1. So this vector right here, the image under this transformation of this vector would be this vector 1, 1 out here. The idea is the height, the y-coordinate stays the exact same, but the new x-coordinate is the sum of the old x-coordinate and the y-coordinate. Note that if we considered a vector on the x-axis out here, since its y-coordinate is 0, the image of this vector would just fall right on top of this vector. Another way of saying that is we got an eigenvalue of 1, and that eigenvalue corresponds with an eigenvector of 1, 0. I guess I should make these blue. Note that this matrix is also invertible. Just think shear back in the other direction. But since the dimension of the eigenspace, which is just 1, is less than 2, that means this is not diagonalizable. Hopefully it's easy enough to see that the only vector that would get mapped to the 0 vector would be the 0 vector itself. That's because the y-coordinate is left unchanged. So to end up with the y-coordinate equal to 0, the original y would have to be equal to 0. But if the original y is equal to 0, then the new x-coordinate is just x plus 0. In other words, x. If you want that to be 0, x has to be 0 as well. What I'm saying is that the nullity here is 0, and therefore, using our rank nullity theorem, the rank must be equal to 2. Before ending this video, which ended up being kind of boring, hopefully it's at least useful for people, let's talk about a 3-dimensional shear. These can be really general, and I guess these could have been a lot more general. Instead of a 1 here, I could have put a k here, in which case the new x-coordinate wouldn't be x plus y, it'd be x plus k times y. But lambda would still be equal to 1, because the only vectors that would not get knocked off their span would be those on the x-axis, and on the x-axis y is equal to 0, and k times 0 is still equal to 0. Maybe I'll write or 1, 0, k1, and leave that as a counterexample for you to explore. The last matrix I want to look at is a 3-dimensional shear. Depending on what axis you want to shear along based on the value in which axis, you can put the constants in different positions. But one example that I think is worth looking at would look something like this. The idea here is we're taking an arbitrary vector x, y, z. Its new y-coordinate is the same as its old y-coordinate. Its new z-coordinate is the same as its old z-coordinate. But its new x-coordinate is not just its old x-coordinate. It's the sum of its old x-coordinate plus some multiple of its old y-coordinate plus some multiple of its old z-coordinate. Sure made that ugly. There, maybe that's a little better. We again only have one eigenvalue. You might assume that it corresponds with the eigenvector 1, 0, 0. And while that is an eigenvector, the eigenbasis is not one-dimensional, somewhat surprisingly perhaps. we can use 0, negative b over a, and 1 as another eigenvector corresponding with this eigenvalue. To see why that works, we can kind of consider the image of this vector using this matrix. When I multiply the first row by this column, I get 1 times 0 is 0, a times negative b over a is negative b, and b times 1 is b. When I multiply the second row by this, I get 0 plus negative b over a plus 0, or negative b over a. And when I multiply the third row by this column, I get 0 plus 0 plus 1. What I'm saying is I get the vector 0, negative b over a, 1, which is exactly what I started out with. So when I take this matrix and I multiply it by this vector, I just get a scaling of this vector, in this case scaling by 1. Geometrically, I don't think it's obvious that this vector is left unchanged by this shearing. I think you need to be pretty good at visualizing these three-dimensional transformations to be able to see that. But algebraically, we can see how it works out. The nullity here is 0, the rank is 3, we're invertible, just shear in the other direction. We're again not diagonalizable. We have one eigenvalue with a two-dimensional eigenspace. I like these examples because I think maybe with the exception of this very last one, you can kind of visualize all of these in your head. And that property of being able to visualize all these transformations, both in 2 and 3 dimensions, and being able to easily figure out ranks, nullities, whether they're invertible or not, eigenvalues, eigenvectors, all that kind of stuff, can make them really easy to use as counterexamples on problems.